Hello and welcome to YMT211, Discrete Mathematics. We are still discussing Chapter 3, Set Theory. This is the second part of the chapter, and today we will be discussing different operations on sets, plus we can say a special topic related to sets in this chapter. So, previously we studied sets and we explained that they are a collection of objects. And distinguishing between these objects is a main characteristic in the set. That's why we separate between each element, we call that individual object in a set element, by commas, and we explain about the set builder notation, the relationship between predicates and sets, and how we could form sets using these predicates and quantifiers. Today we will discuss some type of operations we use in sets. The first one is the union. We can have a union of two sets based on combining all the elements included in either of the sets or in both of them with no repetition. That means if we represent it by the Venn diagram like this, these are the two sets A and B. Now we have elements, they may be in A only or in B only or maybe in between. So the union here brings you or gets you all these elements in the two sets, either collectively, that means in between, or in one of them like A or in B alone. Okay, this is the union. We have the intersection. The intersection is actually the elements that are common between the two sets. It's defined as the elements contained in the two sets. And as I said, again, we don't repeat here. Here we don't repeat. This one is not repeated anyway. If it is in A and in B at the same time, you don't repeat. Just state the element once, and that's the intersection. Again, this one is a bit relevant to the elements which are common, and this is more likely to the elements included in either of the sets or both of them. All right. A direct example or an application example. This is extremely simple. Why? It's just to show you how this thing is applied. Let's say we have these two sets, 1, 2, 3, a set of elements, 1, 3, 5, and another set, 1, 2, 3. So we have these two sets. If we take the union of the two sets, it will be 1, we don't repeat, 2, we don't repeat, 3, we don't repeat. Why? 1, 2, 3. Now, what is included here? 2 is just here, it's not included, but 1 is included in both, so you don't say 1, 1. 1, 1 means 1 in sets, you don't repeat. Repetition here means nothing in sets. Alright, then 2 is just included in set B. Let's say this is set B, and let me take the pen, okay. And then 3 is included in both of them. We don't repeat, we just say 3 in this case, we don't repeat the element itself. 5 is included only in A. So the union would be 1, 2, 3, 5. All right. Now, as I said, repetition in sets actually is not permitted, and it means nothing. If you repeat, it means just one element that you have. 1, if you repeat it a million times, means 1. That's it. Right. Let's take another example about the intersection. Again, the same sets, 1, 3, 5, and 1, 2, 3. If we have the intersection, that means we are looking for the common elements. 1 is common between the two sets, okay. 2 is not. 3 is also common. So the intersection here is just 1 and 3. That's the intersection between the sets. The elements available in the two sets or common in the two sets. All right. If you apply the intersection to two sets and you get phi or empty set, then these sets are called disjoint. That means if we have two sets, let's say here, instead of 1, 3, 5, let's say here we have 4, let's say, and 5, and we don't have these two. What will happen? If we apply the intersection here, what we will get is exactly phi, or an empty set. Why? Because there is no common elements between these two, and in that case we call these disjoint sets. All right, you can take the difference between sets, and the difference here is referred to by complement. The complement of A with respect to B, or the complement of B with respect to A, is exactly the difference between sets. We refer to it by exactly negative sign if you like, or this slash, backslash. Means the difference. It means A minus B here, or actually the elements contained in A and not in B, or the elements contained in B, not in A if you apply otherwise. So the complement of A with respect to B, the complement of B with respect to A, it depends. Okay, so in this case, if we are applying A minus B, this is what we refer to the complement of B with respect to A. So maybe we can consider A as our universal set and B as a normal set, and then we take the complement with respect to A. All right, let's take another operation, and then we see how what kind of practical examples or application examples we have. Now let's see the definition in a mathematical way using a predicate here, in this case quantification. Now look, if we are looking for the difference of the set A with respect to B, or the complement of B with respect to A in this case, now we are looking for elements that are part of A or elements of A, and at the same time they are not elements of B. So this is extremely important. Why? Because we will be using this definition from time to time. So if we say A minus B, or the complement of B with respect to A, we are looking for all elements X such that X is an element of A, and at the same time X is not an element of B. Okay? This is an extremely important definition. Please focus on this one. Why? We have different applications later on when we try to simplify relations or conclude some operations, or validate some operations, in other words. All right, we have another definition. If we assume that we have a universal set, as I said, are all elements included in a particular definition. For example, when I say all students in YMT, let's say 211, discrete mathematics. So all of you, I don't know how many now we have in the system, maybe 30 or so. So if I check all of you, that's the universal set for YMT 211, discrete mathematics. If we say another set, let's say all students of software engineering, that's also a universal set for all students, for the students, those who are actually studying in Department of Software Engineering. All right. So if we are considering the universal set as U, and then we want to take the complement of set A, of course with respect to the universal set, then we refer to this by A bar. And we explain about this in logic circuits, but now we are explaining it back in the context of discrete mathematics. All right. So back again, this is the complement of A with respect to the universal set. We don't say actually with respect to the universal set. Why? Because this is the default case. The default case, we just say A bar. But if you are saying the difference between A and B, that is not the default case. It's just an exception like this case, because we don't know if B is a universal set or not. But if you are considering the universal set, that's the default case, and you just say A bar directly, or the elements that are not in A and elsewhere in the universal set. If you draw it in this Venn diagram, this is A. So where else here? Outside of A. That would be A bar. Okay? That's the idea. All right. That's the definition. A bar is exactly all the elements X that actually belong, or X as elements that are elements of U or belong to U, a universal set such that X is not an element of A. So we left A empty in this case. Exactly, this is why I explained here. It's exactly here, clear, actually more clear. You see, this is the shaded area, that's A bar, and this is A, all other elements other than the elements of A. All right, this is the difference between A and B. Elements included in A, and at the same time they are not included in B, but they have nothing to do with the universal set except that they are in A. Of course, a universal set includes A, but not anywhere else here. Okay, because we are regarding just A in this case with respect to A. All right, let's take another example. This is just an application example in another context. If we speak about the vowels here, the vowels of English A, E, I, O, and U, well, you don't have to worry about Y. It's not exactly the type of debate now whether it is a vowel or not, but let's just say A, E, I, O, and U. These are the vowels of the English alphabet, because other languages have their own vowels. Now the idea, if we are taking A bar in this case, if we are looking for the complement of A, it's all other alphabet except those. It would be from B, C, and etc. You can count, list all of them except for these 5 letters. All right. Let's say if we say A is defined by the set of positive integers greater than 10. That means 11, 12, 13, etc. until infinity. That's the universal set. If we take A bar, it's all other positive integers which are less or equal 10. Means 1, 2, 3. Positive integers start from 1, if you remember. If you don't, try to revise the definition. 1, 2, 3 until 10 inclusively. That's the set. All right. We have these set operations, okay, or sometimes we refer to them by identities. They are like rules applied to sets in this case. If we intersect a set with the universal, of course, what will be the output or the outcome is the same set. That's the identity law. So intersecting a set with the universal set is the same set. A with the universal set as an intersection, the outcome will be A. If we take the union of a set, with phi or an empty set, that's always A. This is the identity laws. We have the domination. Domination means the one that keeps its own identity dominates. In this case, if we take the union of any set with the universal, it remains always the universal, or you take the intersection between any set and phi, it's always phi. We have the idempotent laws. If you intersect A with itself, it's A. If you apply the union of a set with itself, it's always the same set. That means A union A in this case will be A. We have the complementation law, double complementation. If you apply the complementation twice, you take A bar, then take all bar, it will get back you to A. We have the commutative laws. For the commutative laws, we have, you can shuffle the positions. That means which one is set before the operation and will not change the outcome. The outcome will be the same. So if you apply the union here between A and B, or B and A, they are equal. The same goes to the intersection. We have the associativity laws. You guys are familiar. It is like which one comes first. If we have A, then we have the union of B and C, or it is actually represented, or it can be said A, then union B, then all union C. That's possible. The same goes to intersection. We have the distributive laws. For the distributive laws, we have two types. We have the distribution of union over intersection. Okay, so it would be A union B, all, apply the intersection for A union C, or the distribution of intersection over union, and it goes the same. Then we will have the union of the first T, the intersection of the first T, then we have the union for the second T. All right, we have De Morgan's law, same like what we studied in logic circuits, but this is applied to the sets, not just digital values or numerical values. Here, what we are looking for is something more specific. Sets. Here we speak about sets. For sets, De Morgan's law, the complementation of the intersection. If we have an intersection of two sets, all complement, it will be the union of the complement of their individual sets, or the complement of each of them. That will be the union of their complementation process. If you take the other way around, the second De Morgan's law, if you take the complement, or you apply the complementation to A union B, it would be the intersection of their own individual complementation. That means A bar union B bar. The absorption, now the absorption means which one lasts based on this operation. If we have A, then we have the union of A intersection B. That will be the outcome is A. Again, if you do the same way, but with actually we change these operations, the union to intersection and the intersection to union, it will get you back again to A. The complementation laws means the union of an element with its complementation. It is the universe or the universal set all the time. If you take the intersection between a set and its own complementation, there is no any common element here, will be just phi or an empty set. Now, this is the second De Morgan's law. Sorry, this is the first one, not the second one. The first one states that if you apply the intersection between two sets and then take the complementation of the whole process, it's exactly equal to the complementation of A union the complementation of B. How can we prove it? This is easy. Why? Because I said pay attention to the definition before. That gets us to the proof. Now, usually I don't ask proofs in my exams. However, I ask other type of questions. Tomorrow we have a live session. We will discuss about these in details. Please come to the live session. Do not forget. All right. Now, what we are having here is the whole process. How can we represent it in a mathematical way? Because this is the first step in proving anything. Now, the intersection between A and B is what? The intersection between A and B is actually represented by the elements in A and at the same time in B. That means common elements between these two. But in this case, we are looking for the complement. That means the elements that are not common. Okay, so we have the intersection of A and B, but now we take the complementation. That means not those, other than them. The elements that they do not belong to the intersection of A and B. Okay, good. Then the second step, how can we define this one mathematically? Do not belong. If we get it back to negation, it's exactly the elements that they belong to the intersection of A and B, but as negated. If you negate is an element of, it would be not element of. So this is just a basic definition of mathematics. Why? Because it simplifies the process for me. All right. Now, the intersection of A and B here is represented mathematically by elements that are part of A or they belong to A, or elements of A as X, and at the same time, and they're also elements of B. That's the definition of the intersection. Common elements, like if we have these two, A and B, I'm sorry about the bad drawing, but it just simplifies the process. This area, the common between A and B, and, okay? So the negation. Now, you can take the individual negation. If you remember, we spoke about this. Negating and would be or with individual negation of the operations here, whatever we have as separate operation. So it will be not X is an element of A, or not X is an element of B. Now pay attention that and is changed to or, y the negation, flipped it or inversed it. Now, in that case, what does it mean? If I negate X, X is an element of A. If you negate it, that means X is not an element of A, or X is not an element of B at the same time. Okay, when X is not an element of A, it means it's an element of X bar, A bar. Remember this one we just said? This is the definition. If it is not an element of A, of course with respect to the universe, but this is the default, we don't say it, that means it's A bar. Or at the same time, if the element X is not an element of B, that means it's also an element of B bar. And that is exactly the definition of the union. Either an element of A or an element of B. Now A or B, it's A bar, B bar. That's the individual union of these two. And that is the proof of the first De Morgan's law. Usually I don't ask these questions, but they teach you a lot. Why? They show you the representation of this mathematical conclusion or inclusion or whatever you like to call it. All right. This is also proved by truth table. You can go through it. I'll not explain it. You guys are familiar with truth table. I'll just say only one thing. If you remember, I referred to this many times. I said you could start by zeros or by ones. What's important in truth table is always considering all possibilities. What does it mean? It means you can give A 1, 1, 1, 1. Y, actually we have 3 here. So 2 to the power 3, that is 8. So we have 8 possibilities. We can start by 4 ones, 4 zeros, then 2 ones, 2 zeros, 2 ones, 2 zeros, then 1 0, 1 0, and 0. Or if you like, you can start by all zeros, 4 here, 4 zeros, 4 ones, and so on. And if you take the individual union and intersection or whatever, you can prove whatever with truth table. Now, if you are asked to prove, as I said, usually I don't ask proof for laws. Rather, I ask to show maybe simplification of a process. For example, I give you 2 operations and they say show that they are equal. If I do not specify, you will have the right to use truth table or mathematical operations or whatever rules based on the laws that you have or you learned. Or if I specify, you have to stick to what the question is asking. All right. We have a form or a way for generalizing the union and the intersection. For the union, actually, it can be to many sets. And again, it is the collection of the elements that are included of all these sets or at least one of them. Either one of them or in all of them, again with no repetition. Why union? Because we may have common elements between sets, you don't repeat them, that's it. For also the generalized intersection, it's exactly equivalent to the all elements available in between all these sets, between all the sets. They must be common for all sets. If there is not a single element included in all sets together, that means it's phi. No elements, it's an empty set in this case. We have what we refer to by usually computer representation of sets. We have something extremely important. We refer to it by characteristic vector. The characteristic vector is represented by n vector. It's exactly an operation based on the universal set and a subset from this universal set. So we have a universal set represented by whatever. It's not necessarily x1, x2, x3. This is just a generalized form. Okay? And usually we have a subset A from this universal set. But if you have x1, you represent it in A, you represent it by 1. If you don't have it, you represent it by 0. And now look, let's say the universal set x1, x2, x3, x4, x5, x6. So we have from x1 to x6, we have the universal set elements. And at the same time, we have the subset A, x1, x3, x5, x6. So now, we have these 4 elements in A. If we are going to represent the characteristic vector of A, what we are supposed to do is like this. Now look, the first element of A is x1. It's available here. x1 is available. You represent 1. Good. Next, x2 is not available. You place 0. x2 means what? Here, look, in the universal set there is x2, of course, but for A, there is no x2. You place 0. Then, x3 is available, 1. Okay. Then, x4 is not there, 0. x5 is there, 1. How is it there? Here. See? It's here. Okay. Also, 6 is there, 1. And that's it. So, the characteristic vector will be 1, 0, 1, 0, 1, 1. This one. Okay. Sometimes we refer to characteristic vector by bit string. So remember this one, because I usually ask questions about this in the exam. You may have the union or the intersection if you have two actually characteristic vectors. This is possible. Like now we have A and B. So what is A? You have to derive A first. 1, 0, 1, 0, 1, 1. What we did earlier, this one. How about B? Now look at B. 0, because x1 is not there. 1, 1, then 0, 0, 1. These two. Again, how did I get B? Represent the universal set with whatever available in B by 1, what's not available by 0. Now, x1 is not there, 0. x2 is there, common between B and the universal, of course. 1, then again, 3 is available, 1. 4 is not there, 0. 5 is not there, 0. Then 1. Now, if you want to apply the first the union between these two. Now, remember the rules. The union, for union, it is exactly like OR in this case. If you are applying the union between two elements, it applies exactly like OR. 0 union 0, or the union between 0 and 0 is 0. Otherwise, it's 1. Okay. For the intersection now, it is a bit more particular. It is similar to AND. It is only 1 when both of them are 1 or all of them are 1, 0 otherwise. Now look at this. The union here, 1 and 0, the union of these two is 1, these two is 1. One of them is 1 is enough. So these two are also 1, 1 is enough, so it's 1. Here 2 zeros, that's 0. Here 1, so 1. Here also we have 2 1s. One of them is enough, but that means we have 1. Take the intersection, since you sense a 0 or you see a 0, that's directly a 0, 0, then these two are 1, that is 1, there, for the intersection. Again 0, this is 1. Okay, these two are 1s, then this is 1. Right, I believe this is easy because you guys are familiar with this. We explained about it in details before. All right, now we have another type of representation using set, or maybe it has some relationship with set. Actually, it's functions, and I included it in sets because it's somehow relevant. We have a special relationship between, you can say, two types of sets. If we can create some mapping between these two sets, we can refer to them by functions, but based on certain definition. So this definition is referring to a relationship from A to B. Okay, what kind of relationship? Is exactly mapping some elements of A to B. Okay? Or all elements specifically of A to B. All right. So that's the idea. We refer to the elements that to be mapped in this case by specific name. I'll explain about it, and also the mapped elements we specify, or we refer to them by a specific name, and the whole operation we refer to it by a function. Let me just read this definition. You don't have to memorize it, but I will explain a few things. Let A and B are non-empty sets. So this is the relevant part. I said I brought these functions to the chapter of sets. Why? Because it's relevant to the topic of sets. A function f from A to B, again from A to B, is an assignment of exactly one element of B to each element of A. One element of B. So we don't take more than one element at a time from B to A, okay? We write f of A equals B. That means function of mapping A equals B. Now we use the lowercase letters. Why am I explaining this? Why? These are the elements of A capital, or the set. And B also refer to the elements of the capital B, the set. Is the unique element of B assigned by the function f to the element A of A. So if f is a function from A to B, we write, this is referred mathematically, function of A from A to B, or the function from A to B. This is as a function. We refer to it by f, colon A implies B. That means function from A to B. All right, as I said again, we refer to this kind of operation as mapping. Sometimes we refer to it by transformation. Why mapping or transformation? We are mapping A, lowercase a, the element A, to produce B by certain function, or we are transforming A as an input of a function to produce B as an element of the set B. All right, take the specific definition. The specific definition here, we have, if we have a function from A to B, we say A, this A, the set, is the domain. The domain, all possible inputs that can be given to the function. Whatever you can input to the function is the domain, all right? And the image produced, we refer to it by the codomain B. This is a codomain. From whatever you input, all possible inputs will be all possible outputs. That's the codomain. All right. So the image here, when you provide A or you place A as an argument of F, this is an argument, right? Or a parameter to be passed to a function. In that case, we produce this lowercase b. This is the image. We refer to it the image. It's like we are imaging A or mapping A. And A is referred to by pre-image of B. Okay? So again, the image, or sometimes we call it range of F, actually it's the all set of all elements of A here. It should be applicable in this case. All right. Now, the transformation of from A to B is exactly as I said earlier. It's mapping from A to B, or F maps A to B. Like what you see. We have a whole set A, we apply a function, we get another set B. It's like the operation the function is doing, or it does on A. Let's take a direct example. Let F to be the function that assigns the last 2 bits of a bit string of length 2 or greater to that string. What are the domain, codomain, and range of F? And we provided an argument here, or input, or A, lowercase a. I'm sorry about the bad typing. Okay. So here 1, 1, 0, 1, 0. Now think about this. Let me explain the question. The question is like this. It's asking you, we have a function. And this function, what it does, whatever you provide to it must be, now listen, must be of length 2 or greater bits, 2 bits, because we assign bit strings, okay? That means if you provide anything here, it can't be nothing, 0, or nothing at all, or 1 bit, 0 or 1. It should be 2 bits, XX. 2 bits means XX, length of 2 bit, XX. XX means what? It could be 0, 0, 0, 1, 1, 0, 1, 1, okay? Or greater. Greater means whatever length, more than 2. Either 2 or greater, okay? Good. So if you provide this, anything composed of 2 bit or more, then it will create here, it will provide you 2 bits as an output. All right, so the input should be a string, a bit string of length 2 or more or greater. Good. It could be like this, 5. All right, but the output we expect only 2. The output is only 2 x, y. This is the output, or xx, let me refer to it. Input could be of any length of 2 bits or more. It could be more than that, okay? So that you don't be confused. The minimum. So now we're giving you 5. So what will be the output? The output, now before we go further, the output will be xx. Xx what? All possibilities. I'll explain about it. Now the domain, before we go. The domain means what? The domain, all possible inputs here. This is the domain. So all possible inputs are defined by the question. Anything generated or created of 2 bits or more. That means either 0, 0, 0, 1, 1, 0, 1, 1, 1, 0, 0, and you move on. Sorry, 0, 0, 0, and you move on. any possible combination of 2 bits or more. I can't list them. It is unlimited, infinite. Okay? That is why. So any possible here in this case, all bit strings of length 2 or greater, whatever. You don't have to list any. That's enough. So whatever. If you want to provide any definition, you can just put XX dot. Dot dot. That's enough. YXX, it could be 00, 01, whatever. Okay? Continuous. All right. Now, how about the code domain? If we provide whatever to this function, what will be the output? So this is the input. What will be the output? The output is the code domain. The code domain, remember, it provides you with the last 2 bits of a bit string. Okay, the last 2 bits. In this case, what we have 1, 0, the last 2. Okay? But in any other case, if you provide in general, what kind of possibilities do we have? These possibilities can be referred to by XX. XX means what? They could be of 0, 0, okay? All possibilities, then 0, 1, then 1, 0. I don't have to type them there here. 0, 0, 0, 1, then 1, 0, then 1, 1. These are all possible code domain output. But in this case, look what's that assigns the last 2 bits of a bit string of length 2 or greater. But if we are speaking about specifically about this one, only these 2, the last 2, 1, 0 will be possible. Why? It takes the string and it gives you only the last 2 bits. All right. How about the range? So this is the range. I explained about it. Okay. This is the range. All possibilities, all possible values. How about the code domain? As I said, the code domain could be of any combination of 2-bit string 0001 1011, but in this case just 10. Why? Because this is the input. All right, let's move a bit. We have also other practical examples from computation, or you can say programming languages. Think about this method in Java, the floor in Java. The floor in Java receives a floating point input as an argument here. Okay, it's real number, and it removes the point here, the decimal point, and it gets you an integer output. So the inputs here, the domain, all real numbers, and the output could possibly be all integer numbers. So now you make sense of the domain and the code domain. The domain is whatever possible to be input to the function, and in this case it's all real numbers. The output would be all integer numbers. How about the similar representation in C++? We receive also floating point x, and we represent also the output as an integer. This is exactly the idea of domain, all real numbers, the code domain, all integer numbers. All right, now let's go to a bit more specific definitions. The specific definition here is referring to something related to what we are mapping, or what kind of images do we have. Are we consuming all images or not? If we are not consuming all images, images means what? The elements of B, what we are mapping. If we are not consuming all of them, what is the set of all images? Okay, so this is the idea. Now, sorry, think about this example. Without going through the definition, let me just go to the example. The idea would be clear to you. Let A equals set of A, B, C, D, and B set of 1, 2, 3, 4. And we have a function from A to B here. Function of A we refer to the set A. Okay? Function from A to B, that means function from A as a set to B as a set. Okay, f of A equals 2, f of B equals 1, f of C equals 4, f of D equals 1, and f of E is equal to 1. What's the image of the subset S? Now we have a subset from B, B, C, D. So the image, now we look only for specific part from A, B, I'm sorry, not A, B, C, and D. Subset of A, we look for their image. So in order for you to get it, look at the image here, 1, f of B is 1, so this is the first element. Then f of C is 4, second element. F of D is 1, again we have it here so you don't repeat. It would be 1 and 4, that's it. Alright, this is a direct example, it's easy actually, it's not difficult. We have two important definitions and we usually, 99% of exams, we bring questions from those. We have actually three, not two, three main definitions, but the third one is based on the first two. Now I'll explain. We have the definition of 1-to-1 and the second one on 2, and then both together at the same time. 1-to-1 is exactly when we have a function from A to B, and at the same time we have B is represented by just one, the set B, that means the elements of set B are represented only by one A, or element of A. Means what? The function f itself is not repeating A as an element for more than one B. Meaning what? Only if A equals to B, that is the case when we have 1-to-1. Other than that, it is always not repeated. If you take f of A1, it will give you B1. F of A2, it will give you B2, and so on. This is 1-to-1, or sometimes we refer to it by injunction, or sometimes they refer to the whole action by injective function. Okay? So remember this definition. Well, maybe you are not quite sure. I'm not really sure about what you are saying. Let me clarify it by a simple example. Now think about f as a function from A, B, C, D. All right? So this is A, okay? Set A. And then we have the set B, 1, 2, 3, 4, 5. So this is set B. If you want to take B, I'm sorry. If you want to take, let's say, a mapping, this is an assumed mapping. F of A equals 4, F of B equals 5, F of C equals 1, F of D equals 3. Is it 1-to-1 or not? Now we need to see. F of A, is it taking only one value? Yes, 4. It's not taking any other value here. All right, good. How about F of B? Yes, 5. There is no other. F of C, 1. There is no other than that. F of D, 3. So F of A is only is taking you one value only from the codomain. F of B, also one value. F of C, one value. F of D, one value. So those are consumed by different A's here. A's means elements of A. A1, A2, A3, for example, or ABC if you like, from set A. And this is set B. All right. Okay, so this is the idea. Since we are having different mapping, different output for the mapping, that is 1-to-1. This is the definition. It takes different values, and that's the definition. All right, let's take another more practical example, something that looks more mathematical to us. Determine whether the function f of x equals to x squared from the set of integers to the set of integers is 1-to-1. Now, if you plot x squared is like this, is something like this. Oh, I'm sorry, this is not good. Let me try to clean this one. Okay, I'm just trying to make it like around the center. Okay, it's like this. It's like this. Okay, the drawing is not very good, but it's like this. Okay, so now we are looking for this x squared. Is it 1-to-1 or not? Now 1-to-1, that means if we are mapping from A to B, we should get only one value for each A. Now look, this is the y-axis. We have the reflection of this point, which is equal to this point exactly around the y-axis. This is like reflection. Imagine it's a mirror. This one is reflected here, or this one is reflected here. So we have two elements around y-axis. That makes what? That makes the function not 1 to 1. As a proof, now think about it. If we say f of 1 integer, we speak about integers, f of 1 is equal to 1 squared, that's 1. F of minus 1 squared is equal to 1 also. So if this one is 1, okay, as a value, it takes you to 1 and it takes you to minus 1. So here a, this lowercase a, is assigned to b and maybe c in the codomain. And that violates the concept of 1 to 1. So in brief, if you have a function that is reflection or it is centered around the y-axis, take a shortcut. It's not 1 to 1. Anything that is divided into half around the y-axis. So y-axis is dividing it. Now look, we have half here, exactly half here, and then half here. Okay, so that's why this function is not 1 to 1. Let's take another example. Determine whether the function f of x equals to x plus 1 from the set of real numbers to itself, that means to real numbers, is 1 to 1. It is. How do I know? Well, you can apply, but we have an easy way to do that. You can draw it, if you can plot it. Now, I'm not sure if you can see or not here, around here, because usually this one does not display in drawing. 1x plus 1 is something like that. This, if we place x to 0, then y will be 1. If we place y to 0, then x equals to minus 1. So here we will have something like this. When x is 0, y is 1, okay? When y is 1, x is minus 1, something like this. This is an approximate, okay? I'm not very talented at drawing with mouse, okay? So something like this. What are we going to have is like a straight line intersecting with x and y, but it is not centered around y-axis. This is y, or f of x, okay? F of x. And this is x, okay? So we have this not centered around y. It's not divided equally by y. Rather, it is somehow centered around the origin. It's just shifted upward like this little bit. So if you have anything centered around the origin or just intersecting with x and y, x-axis and y-axis like this as a straight line, then definitely it's 1 to 1. Whatever value you give to a or x here, it will have a unique output. It won't be repeated. Why? Because there is no reflection. How about, let me give you another example. How about the absolute value? The absolute value of x. Is it 1 to 1 or not? Absolute value is very similar to this parabolic, but it's just a straight line from here coming upward and another straight line coming upward here. So definitely it's around y-axis and it's not 1 to 1. You can think about all other functions. We will have some other practical examples to run also in separate session, not now. Just these are common examples that I usually explain while going through the theory in this chapter. Okay, let's carry on. The second definition, I said 1 to 1, we explain about it. No repetition for the A, the element of the capital A, that means the element of the domain for the codomain. All right, how about onto? Onto is defined as, again, we have a function from A to B. We can define a function as an onto or surjection if every element in B, there is, for every element in B, of course, here B, capital B, we have an element of A. That means all elements of B are consumed. if all elements of B are consumed, then that is a surjective function. All right, what does it mean? It means, like, let's take a direct example. This is a very easy example, like earlier. A, B, C, and D for you know, the the domain, and we have 1, 2, 3 as the codomain, or B. Now, if we are mapping f of A equals 3, f of B equals 2, f of C equals 1, have we consumed all these? Yes. 1 is here, 2 is here, 3 is here. We have consumed them. That is on 2. But let's say if we say f of A equals to 3, f of B equals to 3, f of C equals 1, then we haven't consumed them. That means it's not on 2. All right. Let's take another example. Let's take the example we explained about it earlier. Let's say the function f of x equals to x squared for the set of integers, from integers to integers. That means the input here is integer and the output is supposedly to be integer, okay? Now we say like this. Is it onto or not? And in this case, if you think about it as an onto, now look, the set of integers includes -1. Can we have -1 in the codomain, sorry, in the domain for -1 in the codomain? No. How? Now think about it. We said set of integers to the set of integers. That means the domain is integers, all integers. The codomain is all integers. Take it in a very easy example or very easy representation. X squared equals, let's say, -1. Do we have such a thing in integers? Of course not. So for set of integers, there is no representation like this, but yet we say that for all integers, then it is not on 2. This is not on 2. Now, if you have a function that satisfies the two relationships, 1 to 1, and at the same time it's also on 2, then this function is called correspondence or bijection. 1 to 1 correspondence or bijection. Usually we ask about bijection in the exam, why it combines both the surjection or also the injunction, all these two. All right. If we ask, then you have to start by 1 to 1, and if it is correct, then you go to onto. If 1 to 1 is not correct, if it's not guaranteed, then it's not bijective directly. You don't have to go and check for onto. All right. Let's take a direct example. Let f be the function again, a, b, c, then we have a, and then we have b, 1, 2, 3, 4. Look at this. F of a is equal to 4, f of b is equal to 2, f of c is equal to 1, and f of d is equal to 3. Is it bijection? Bijection, by definition, means 1 to 1 and on 2. 1 to 1, now look. F of a is taking 4, okay? F of b is taking 2, fine. F of c is taking 1, and f of d is taking 3. There is no repetition of these elements for 1a. So great. There is no centering around y-axis. Good. That means it's onto. It's 1 to 1, sorry. For onto, have we consumed all the codomain? We have 1, we have 2, we have 3, we have 4. Yes, it is 1 to 1 and it is onto. That's why it is bijective or bijection in this case. All right. This is like the similar representation of 1 to 1 and onto. 1 to 1, as I said, it must take unique elements for each of the domain from the codomain. That means mapping the domain to unique codomain values. We can't have a back again to here, for example. So a takes 1 and takes 3. That is not onto, 1 to 1, sorry. But onto means what? This one is not consumed. Since it is not consumed, it's not onto. Consumed, that means used by the function, mapped by the function. Onto, all of them must be mapped. You can have like an element twice, is possible. By the way, I used a. A is already represented. I can't represent it again. If I represent it again, it won't be a function in this case, okay? But let's say a value, two values here represent the same image. Two values, like what we did earlier, 1 and -1. They represent 1 as an output. 1 squared is 1, minus 1 squared is 1 also. Same like what we did x squared earlier, and that is very similar. Not this one, I mistakenly wrote it. Sorry, this one doesn't represent the definition of a function. I'll explain about it in a while. On to not 1 to 1. Why not 1 to 1? We have 2 represented by 2 elements, A and D. Now look, that's important. Okay. Now think about 1 to 1 and on to 1 to 1. That means each element is represented uniquely by a codomain value. Not necessarily they are coincided. That means A takes 1, B takes 2. Not necessarily, but uniquely represented. Then it is also onto why all these elements are consumed. We have for each one a pre-image. If it is neither 1 to 1 nor onto, means what? We have A and C represented by 2. That means it's not 1 to 1. We have 2 elements represented by 1 image. And at the same time, we have one value here not represented. Okay. Now, the one I made mistake earlier. If we have A represented by 2 elements at the same time, that's not a function. It violates the definition of a function here. Why? Because we are mapping A to a unique value. We can map B to the same value. Yes, that's possible, but not A to another value. That means we don't have exactly a function. The function is not well defined here. We don't have a unique value for it in this case, and we don't want to go to that special type of relation. All right, this is the end of the session. We have just one session left for this chapter, and until I explain that one or until I make a video for it, have a good time. Goodbye.